now the whole thing is such, the mathematics is arranged in such a way that it makes sense to pass to 0 with the with Planck parameter. That's a deformation quantization, and we get exactly the classical part characterized or described by the Poisson. But now we have to go to the quantization. We have to take a representation of the C star Weil algebra with Planck parameter H. So the field vector is that way. Up to there, we had no quantum field theory. We have a sort of a requantization. But this part here, that's the bunch of quantum observers. But now, of course, we can do this for the Heisenberg group. We take this theta h as this point evaluation, then take the representation and get a specific, since we work with this part here, we have indicated the representation as coming from this Weil algebra with this scale parameter. Now also the Weil elements can be written in this form with a sort of a classical field operator. Now you see that the brackets here.
What is this phi naught?
That's the field. That's a sort of a field operator. But of course, it's not representation to the. It's not linked to the representation yet. But that will come soon. But it's the main part of the field operator anyway. And commutation relations of this type, that the commutator is a multiple of the one, actually of the imaginary part, in such a way that the multiple is given by the symplectic structure, the PQ in P times Q on the real line. That's called the canonical commutation relations. And they steam directly out of the Weil elements. And here we take now the representation, form one parameter groups. Think of the representation of being nice, strongly continuous. So they have continuous one parameter groups, and then Stone's theorem tells that one has generators, and in fact that's the one parameter group. Again, a bit modified by that phase factor. That one parameter group differentiated gives the field operator, one we already had, plus this part here coming from the center. And that links to the question, do commutative things always mean classical things? If one has a commutative algebra, is that made up of classical things? That's one of these classical parts coming out of the field. And you see that the generators here of this one parameter group satisfies again this sort of commutation relation. Canonical commutation relations. Now the question is, does this link somehow with what physicists do?
Can I just ask a question?
Yeah, please.
What's happened to the original vector field you started with? Have you sort of averaged over that, or?
The symplectic structure is an average over it, and due to that, due to the fact that I worked on sections, on the space of sections, I looked at the points in total all the time. You had at the very end of your talks this morning also sections.
Yes.
That means implementing the bottom into the bigger space.
Right. Right.
And the section is then a function, of course, on the manifold I'm looking at, and the vector field enters this space of section by this symplectic form. So the characteristic part from the vector field, as far as length of vectors is concerned, is hidden in the symplectic structure. The directions of the vector field, this projective part, is hidden in the complex line bundle and in the Heisenberg group bundle. So both together, the bundle marking directions and the symplectic structure characterizing the field strength are encoded in this algebra made up of sections. And this, of course, replaces a sort of a mean, if you want. The section goes over all points. And then, of course, this is truly a mean of the mean symplectic structure, if you want. Now, of course, the story goes on, but I don't go on too much, just give me a minute. We have constructed these field operators, these generators of the one-parameter groups. The generators so that the whole thing can be written like as a sort of a phase factor, but of course there's an operator in it, and very general type of phase. The question is, has it something to do with what physicists do? So far it's mathematics. I never talked about physics. Now, let's go to physics. And for a mathematician, let us assume that what physicists do with GNS representations, that's physics.
Perhaps.
Okay, that's why I want to assume it. I'm not allowing me to judge the work of physicists. I'm just a mathematician. Now, if you have a state and a state space, you can construct in presence of density operated GNS representations. Every representation of this type is a sum of GNS representations. On the other hand,
Why is that? Is that obvious?
no, that's not obvious. My friend, the physicists, made the proof.
Oh.
Good friends.
I'm just a mathematician. Our work was done there. In the day. And on the other hand, you can do the following. You can take a positive function and then look at its state and then construct out of that state the GNS representation, or else a while element. While elements. And these while elements quantize then in this way, or else, with the GNS representation, and that fits. So that's just another way here of talking about field quantization of the physicists. Another way in the sense that the internal variables here produce the central ingredient, namely the C-star algebra of the quantization.
Why do you say internal?
Yeah.
Because it's still in your free space. It's
That's
just
right. But as far as the vector field is concerned, the vector field talks only about a vector, not about
okay,
the
so
plane.
you're looking at it in terms of the vector field itself.
That's
You're
right.
more or less saying, forget about the manifold, yeah?
That's right. That's
We're
right.
just taking the
Yeah,
field.
you can say it exactly in this way. Or else in terms of the example of the pointing vector and the plane wave.